Hey everyone, Professor Baldwin here, and today we're going to talk about rational functions. Remember that a rational function is just a function made from two polynomials, one dividing the other. So it's a fraction. Remember that the domain of a function, especially a rational function, is any value that does not make the denominator 0. So this first example, we want to find the domain. To do that, we need to factor the denominator. So we're going to take x squared minus 6x plus 5. We want to know when that equals 0. And to do that, we need to factor it and then solve it. Leading coefficient is 1, so we know that our first term in each factor is going to be x. Then we're looking for the two numbers that multiply to 5 but add to negative 6. That would be negative 5 and negative 1. That tells us that our zeros here are x equals 5 and 1. These are the two values that will make the denominator 0, and you cannot have a denominator of 0. So these values are not in the domain. So we need to write the interval notation for the domain that does not include those. Well, let's put them in the right order, 1, 5. That means we can go from negative infinity until we get to 1. Then we have to stop. Then we can go from 1 until we get to 5. And we stop. And then we go from 5 through infinity. That would be the domain for this rational function. Now, another thing that's really helpful with rational functions are the asymptotes. Asymptotes are lines that a function approaches but never touches. And a vertical asymptote then would be that vertical line that the graph is going to approach, and a horizontal asymptote would be a horizontal line. So to find the vertical asymptote, what you're going to do is you're going to factor your whole polynomial, numerator and denominator. So for this example, x cubed, it just stays as x cubed in the numerator. And the denominator, well, we have a GCF of x, so factor out the x first, and we have 2x squared minus x minus 3. Well, we need to see if we can factor this polynomial that remains. So I'm going to do some quick notes on the left-hand side here. 2x squared minus x minus 3. Since we have a leading coefficient that isn't 1, we're going to use that key number method. So a times c equals negative 6 and b equals negative 1. So we're finding two numbers that multiply to negative 6 but add to negative 1. And those would be what? Negative 3 and a positive 2. Remember, that tells us how to rewrite that inner term. So we're going to have 2x squared. Let's do plus 2x minus 3x minus 3. Then we factor with grouping, and we have 2x times x plus 1, and we have minus 3 times x plus 1, which factors to x plus 1 times 2x minus 3. Okay, let's rewrite our rational function again. X cubed is still in the numerator, and then we have x times x plus 1 times 2x minus 3. Now you're going to simplify the numerator and the denominator. They have an x in common, so simplify that out. You're left with x squared in the numerator, and then x plus 1 and 2x minus 3 in the denominator. Now that you have totally simplified, your vertical asymptotes are the zeros from this denominator. So x plus 1 equals 0 and 2x minus 3 equals 0. The first one tells us there is an asymptote at x equals negative 1, and the second one tells us there's an asymptote at x equals 3/2. Now, vertical asymptotes, they take a little bit of work. Horizontal asymptotes, a little bit easier, but there's more rules to remember. So for the horizontal asymptotes, you're comparing the degree of your numerator and the denominator. If it's the same, you're going to end up with a line that is equal to the quotient of the leading coefficients. If the degree of the numerator is less than the denominator, you get y equals 0 as your horizontal asymptote, so that is your x-axis. And if the degree of the numerator is greater than the denominator, there's no horizontal asymptote. Okay, so our first example here, the degree of the numerator is 2 and the degree of the denominator is 2, so the degrees are the same, so we're going to have a line y equals the leading coefficients. The leading coefficient of the numerator is 3 and the denominator is 4. So y equals 3/4 is going to be our horizontal asymptote. For example 2, the degree in the numerator is 2 and the degree in the denominator is 4. The numerator is less than the denominator, so y equals 0, or the x-axis, is going to be your horizontal asymptote. See, a little bit easier to calculate, but a lot more rules. Now, a third asymptote you can have is an oblique asymptote or a slant asymptote. It's just like the name says, it's a diagonal of some sort. And this is when the degree of the numerator is 1 greater than the degree of the denominator. And look how you find it, long division. So you're going to use synthetic division here. But again, it's only if the degree of the numerator is 1 greater than the degree of the denominator. Here, our numerator has a degree of 2, our denominator has a degree of 1. We have a winner. We're going to do some long division. So we're going to take our denominator, which has a 0 of -3. That goes in our synthetic division box. Then we're going to write the coefficients for our numerator, 1, 4, and -1. Draw your division line and a vertical line at your constant. Remember, you bring down that first coefficient, you multiply it by the divisor, then you add vertically. Multiply and add. We're going to ignore this remainder, and this result, which is x plus 1, is going to be the equation for your oblique asymptote. Not too bad, because we became masters of synthetic division. Okay, we need to piece all of this together in order to be able to graph a rational function. So let's go step by step. Step 1, we want to find any real zeros of the denominator. Well, to do that, we need to take the denominator, x squared minus 9, equal to 0, and solve it. So that's x squared equals 9, or x equals plus or minus 3. This is going to give us our domain, right? These values, 3 and -3, are points that we cannot include in our domain. So our domain is going to go from -infinity until we get to -3. Then it's going to go from -3 until we get to +3, and then it'll go from +3 on to +infinity. Now we can sketch our vertical asymptotes. Remember your vertical asymptote? You're going to take your numerator and factor your denominator. You're going to simplify, and your vertical asymptote is going to be wherever you have a 0. So x equals 3. I'm going to draw my asymptote in a dotted line here at x equals 3. So this is x equals 3, and that is our only vertical asymptote. Okay, step 2, we need to find horizontal or oblique asymptotes. Well, we don't have an oblique asymptote because the degree of the numerator is not 1 greater than the degree of the denominator. So we need to find the horizontal asymptote. And to find the horizontal asymptote, we need to compare our degrees. We have a degree 1 in the numerator and a degree 2 in the denominator. So if the numerator is less than the denominator, y equals 0 is going to be your horizontal asymptote. So again, let's do that in this dotted black line. So this is y equals 0, which is going to be your horizontal asymptote. Now we're going to go to step 3. Find any zeros of a function by finding zeros of the numerator. So when is the numerator 0? X plus 3 equals 0. Well, that would be when x equals negative 3. Okay, but notice that x equals negative 3 is not part of our domain. So that means at x equals negative 3, there's going to be a hole. The graph is not going to go to that part. And now we're moving on to step 4. We need to find f of 0. So here it's function g. So g of 0 is going to be 0 plus 3 over 0 squared minus 9 equals 3 over negative 9 equals negative 1/3. This gives us the point 0, negative 1/3, or our y-intercept, which is roughly right here. Well, this isn't really enough to draw our function. We can go from this y-intercept to the left because we know we're going to approach that y equals 0 asymptote, but we're not going to actually touch it. But what happens to the right? And what happens in this upper quadrant up here? So for that, we're going to make a little chart and pick some values and see what our function does. So we want to see what's happening on the right side of our line. So let's choose x equals 2. And when we substitute that in to our function, we're going to get 5 over negative 5, which is negative 1. So when x is 2, we get a value of negative 1. So that means our graph will touch that point, and then it's going to approach that vertical asymptote. Okay, we finished the left chunk of the graph. Now let's look at what happens to the right of that vertical asymptote. So we want to pick a value over there. What if we pick x equals 4? That would give us 7 over 16 minus 9, or 7 over 7, which is 1. So the point 4, 1, that would be this point. That is actually enough for us to get an idea of what happens, because to the left of that point, it's going to approach that vertical asymptote. And to the right, it's going to approach the horizontal asymptote. So there we were able to make a hand-drawn graph of this rational function. Okay, what if you're told some things about a rational function, so some conditions, and you need to come up with the actual function, so the equation? Well, what do we know? We know vertical asymptotes. Well, vertical asymptotes are going to give us our denominator. Okay, so let's set this up as a fraction. The vertical asymptotes give us part of our denominator. X equals negative 4 is the same as x plus 4, and x equals 5 is x minus 5. So we know that we have these two binomials in the denominator. Okay, now what about the horizontal asymptote? Y equals 3/2. Well, in order for it to be y equals 3/2, that means the degree of the numerator and the degree of the denominator needed to be the same. So we know that our denominator is an x squared, right? When we FOIL this, we get an x squared. So that means our numerator needs to be an x squared. And then the 3/2 are your leading coefficients. Okay, we still need a little bit more to fill in that numerator. The x-intercept is -2, 0. Well, the x-intercept, we find that by solving the numerator. So the numerator, in order for x to equal -2, x plus 2 is going to be a factor. Okay, so notice our numerator. We have x plus 2, which at this point, with that leading coefficient of 3, is 3x plus 6. That doesn't give us the much needed x squared. So we need to throw in another x in that numerator in order for the degree of the numerator and the denominator to be the same, which is required with that horizontal asymptote. Now this satisfies everything, we just have to expand it. So expanding the numerator, we're going to distribute the 3x and we get 3x squared plus 6x. And in the denominator, we're going to have 2 times, we need to FOIL these two binomials. That is x squared minus 5x plus 4x minus 20. And we're going to simplify and multiply by 2. And we'll keep the numerator. So our denominator is going to simplify to 2x squared minus 2x minus 40. Just make sure you're using all of the little clues and hints that you get. You might need to make some notes like this x squared note that I had to make on the left-hand side, just to make sure that you incorporate everything you need to incorporate. I know that was a lot. If you have any questions or you come across a problem you want help with, leave it in the comments and I'll include it in one of my videos.